What do you see when you look in a mirror? A perfect reflection or just a symmetrical illusion? In reality, our bodies are not as symmetrical as they appear. The two halves of our face seem like copies of each other. However, when we look closely, there are differences. For example, our eyes differ in both size and alignment. So are our arms and legs. These details are so small that we often can't notice them. The mirror reverses all these small differences. It creates a sense of balance in our minds. So there is a symmetry between our real image and the reflection in the mirror. If our left eye is smaller in reality, in the mirror, this corresponds to our right eye. If our right arm is thicker, we see our left arm as thick in the mirror. Just like humans, the universe is not symmetrical either. For example, time only flows forward. Matter is much more dominant than antimatter. Even the rotation directions of distant galaxies are different from each other. It's as if there is a cosmic asymmetry. So, could there be another universe that turns all these imbalances into symmetry? For instance, a universe where time flows backward and antimatter is more dominant than matter. According to scientists, this is theoretically possible. Our universe could have a symmetrical counterpart. Now, this theory didn't just appear out of nowhere. I didn't prepare this video out of nowhere either. There is a strong basis behind this idea, symmetry. Because as humans, we love symmetry. We always seek beauty and aesthetics in it. Most things in nature that are pleasing to our eyes are symmetrical. The wings of a butterfly, the fins of fish, even the hexagonal structure of a snowflake all possess perfect symmetry. For many years, scientists thought that the fundamental workings of the universe also had such a balance. Even if the direction of a particle in space changed, nature was expected to behave the same. Even if matter and antimatter swapped places, the universe's response should have been the same. Even if time flowed backward, the laws of physics were not supposed to change. That's what they thought. Because at the core of physics, there are three fundamental symmetries. CPT, charge, parity, and time. When these three are applied together, the laws of physics are not violated anywhere in the universe. I will explain what I mean with examples. But first, I want to talk about what these letters actually represent and why they are so important. Don't worry, I will try to do this by simplifying as much as possible. So, prepare your tea or coffee. We are embarking on a journey in pursuit of symmetry. Charge symmetry means the swapping of particles with their oppositely charged twins. So what does this mean? In the universe, every matter has an antimatter counterpart. For example, electrons are negatively charged. Their counterpart, positrons, are positive. So the antimatter of an electron is a positron. You can think of these as the symmetrical shadows of the universe. If the universe is truly symmetrical, the result of a physical experiment we conduct with a particle should be the same when conducted with its antimatter. In other words, even if the electric charge changes, the laws of nature should not change. Our second symmetry is parity. If we reflect a physical event in a mirror, this reflection should operate in the same way as both in the real world. For example, if we throw a ball upwards with the right hand, in the mirror it appears as if it was thrown with the left hand. But the laws of physics do not change. Therefore, mirror symmetry is preserved. The last one is time symmetry. The laws of nature should work the same way whether time flows forward or backward. Let's say we are recording an event on video. Let's continue with the ball example. We threw the ball into the air and then it fell back into our hand. What happens if we rewind this video? The ball would appear to come down and return to our hand. So, is this situation valid in terms of the rules of physics? Theoretically, yes. Of course, in the real world, such a thing is not possible. But if it were, everything would still happen within the rules of physics. It would just flow in the opposite direction. Physicists thought that these three symmetries would never be broken. But things didn't go as perfectly as they thought. First, mirror symmetry was broken. Physicist Chen Shangwu and her team conducted an experiment in 1956. They cooled atoms called cobalt-60 to very low temperatures. They brought them to a point almost close to absolute zero. Thus, the spin directions of the atoms aligned. In other words, they were aligned to always point upwards. Then they observed which direction the electrons were emitted as these atoms decayed. If nature preserved mirror symmetry, the electrons should have spread equally in both directions. But guess what happened? The electrons moved in the opposite direction to the spin of the atoms. Now, if we reflected this experiment in a mirror, the direction of the electron's movement would not change. Because a mirror only swaps left and right, it cannot reverse time, but the spin direction of the atoms would reverse. Just like how the right hand appears as the left hand in a mirror. This result left the scientific world astonished. The universe is not as symmetrical as we thought. Nature can distinctly differentiate between left and right. This is one of the pivotal moments in the history of physics. In fact, the physicists who proposed the theory, Sung-Dao Lee and Chen-Ning Yang, were awarded the Nobel Prize in 1957. However, the person who conducted the experiment, that is, who tested and confirmed this idea, Cheng-Sheng Wu, did not receive the Nobel Prize, although she was honored with the Wolf Prize in Physics in 1978. But this event is considered one of the greatest injustices in the world of physics. Anyway, let's get back to our topic now. Physicists who saw the breaking of mirror symmetry had another question in mind. What if the universe not only distinguishes directions, but also makes a distinction between matter and antimatter? This brings us to charge symmetry. What did we just say? Even if we replace a particle with its oppositely charged twin, nature should behave the same way. In other words, the universe should not make a distinction between matter and antimatter. But some experiments showed that this is not the case. While a particle veered in a certain direction, its anti-twin sometimes chose a completely different path. These small differences showed that nature is not neutral towards matter and antimatter either. So, charge symmetry was also broken. Scientists searching for symmetry in the universe have not lost hope yet. They said, okay, mirror symmetry is broken. Charge symmetry is broken too. But maybe both are preserved simultaneously. Things did not go as expected here either. In 1964, two physicists named James Cronin and Wal Fitch conducted an experiment on particles called K-mesons. They examined these particles and their anti-twins. Both were transforming into other particles over time. But something interesting was noticed in this transformation. The K-meson and the anti-K-meson did not behave in the same way. The distribution of the resulting particles was also different from each other. This difference showed that there was a distinction not only between matter and antimatter, but also between right and left. In other words, both charge and mirror symmetry were broken together. From this point on, scientists thought as follows. Even if all other symmetries are broken, CPT symmetry must be preserved as a whole, because all the laws of physics in the universe are based on this symmetry. Numerous experiments have been conducted to date, and no contrary result has been found. At CERN, protons and antiprotons were compared. No difference was found. In America, the magnetic properties of electrons and positrons were measured. They came out exactly the same. Even in experiments where time was reversed, CPT remained intact. Nature still preserves this triple combination. But these experiments are always at a microscopic level, that is, at the level of particles. When we consider the universe as a whole, there is no symmetry, as we might think. Time always flows forward. Galaxies are not distributed equally in all directions in space. Right after the Big Bang, matter and antimatter were equal, but then matter prevailed. It's as if the universe somehow eliminated or hid antimatter. All these examples show that nature takes sides on a large scale. To explain this imbalance, physicists first asked this question. Could there be a twin of the particles in the universe that we cannot see? In 1966, Russian physicist Igor Kobzarev and his team gave a rather radical answer to this question. They said yes, these particles could have mirror twins that behave just like them, but do not interact with us. They named this idea mirror matter. This theory later inspired dark matter research, and the following question began to be asked. Is the dark matter, which makes up 27% of the universe, composed of mirror particles? In other words, could dark matter be mirror matter itself? Mirror matter was thought of as a hidden shadow of the particles we know, but some physicists took it a step further. Could the entire universe also have a mirror? In 2018, physicist Neil Turok and his colleagues wrote an article. They proposed the CPT symmetric universe, a cosmological model based on CPT symmetry. They suggested that there could be a mirror universe corresponding to our universe, and based this on mathematical modeling. Interestingly, this theory does not violate any laws of physics. On the contrary, it reinterprets them from a symmetric perspective. Look at these words from Neil Turok. The combination of you and your mirror image is more symmetric than you alone. You know how we said at the beginning of the video that our two eyes aren't symmetric, but when we look in the mirror, the symmetry is completed. According to the standard cosmology model, the Big Bang is considered the beginning of our universe. But according to the mirror universe theory, it could also be the beginning of another universe. So, like a point of symmetric divergence. One of the twin universes emerging from the Big Bang, namely our universe, contains more matter, while the other universe might be largely composed of antimatter. Now let's imagine turning an hourglass on its side. The narrow part of the hourglass, or the neck, represents the Big Bang. One cone is our universe. Here time flows forward. Matter is more dominant, while the other cone is the mirror universe. Here, time flows in reverse. Antimatter is more dominant, but don't perceive it as time travel. In that universe, time progresses normally when viewed internally. We just perceive it as if it operates in reverse. If an observer from the same universe could look at us, they would probably think that our time is also flowing backward. The mirror universe theory is not just an idea of aesthetic symmetry. It also has the potential to solve many cosmological problems. For example, physicists have observed that the universe is almost geometrically flat on large scales. However, there is a problem here. If the universe had started expanding randomly after the Big Bang, it would have had to collapse and disintegrate rapidly in a very short time. Yet it remained flat with miraculous precision. Physicists tried to explain this situation with the theory of inflation. The universe experienced an extremely rapid expansion, or inflation, at a very early stage. This inflated the universe like a balloon, flattening it. Just like a small wrinkle on a balloon smooths out when the balloon is inflated. But this raises another question. What initiated this tremendous expansion? According to the mirror universe theory, the conditions at the beginning of the universe start automatically in a flat and balanced manner. Because thanks to CPT symmetry, the universe behaves like a single symmetric structure. At the starting point, this theory also provides a solution to the question of what existed before the Big Bang, which science has not been able to answer until now. Because according to this model, there is both a before and after the Big Bang. In one, time flows backward, and in the other, it flows forward. In physics, there is also a problem known as the Hubble constant problem. The mirror universe theory provides a solution to this problem as well. The value that measures how fast the universe is expanding is called the Hubble constant. But there is a problem. When we calculate this constant by looking at the early universe, the value we get is very different from the value we get when measuring the current universe. Moreover, this difference is too large to be explained by measurement error. Could the reason for this difference be the gravitational effect of another universe? Scientists have been trying to measure the lifespan of neutrons for a long time. However, two different measurement methods show different lifespans for the neutron. According to one, it's 879 seconds, and according to the other, it's 888 seconds. Although the difference seems small, it is a significant issue on the precise scales of physics. Some scientists think that this difference is due to neutrons, sometimes transitioning to another universe. The mirror universe theory sounds exciting. In fact, as I mentioned earlier, it also provides consistent solutions to many cosmological problems. However, as with many theories, in physics, we have a similar issue with this one, a lack of observation. We neither have a mirror universe that we can observe with a telescope, nor a method to test it. Moreover, being mathematically consistent does not always mean that the theory is correct. Observation is a very important concept in science. So, if we cannot test a theory, it becomes difficult to classify it scientifically. But let's not forget, we also cannot see dark matter, but we are sure of its existence. If it didn't exist, galaxies would fall apart, and stars would be flung into space. The universe could not exist in the structure we know today. Perhaps the mirror universe is something like that. We can't see it, but maybe one day, we might encounter its effects. Today, many theoretical physicists are trying to simulate this model with supercomputers. How would the initial conditions of two symmetric universes diverge at the Big Bang? How would this divergence affect the large-scale structure of the universe as we see it today? These are the questions they are seeking answers to. We cannot know what the outcome will be, but there is one thing we do know. The idea of a mirror universe emerged from humanity's passion for symmetry. Our eyes have always sought it. We have always seen beauty and aesthetics in it. But perhaps we forgot something. It is those asymmetries, our imperfections, that make us who we are. The universe we live in is the same. It appears perfect, but harbors many issues. Perhaps that's why we admire it so much.